good, guys. We have attendance. 1201, the code. Don't forget that. Okay, let's get started. So we have a discussion. I want you guys find some application of this course based on what you are working. If you have a project, if you don't, just figure it out, something. And I want to have a discussion between you guys to see how think about this course and like in terms of applications, whatever. I want to put like a couple of paragraphs, not too much, till tomorrow. And then till Friday, response the others. I want to see this regarding, discussion, pre-discussion. Everybody talk about others, projects, and I like that. So what we want to talk today, what we had last class was about estimation. You're still in that part. That's an important part of this course. It's one of the outcome. The main outcome of this course is to teach you and you learn how use material in this course to predict something, to estimate something. Not normal estimation. So the normal prediction, we call it blind estimation. You just can get average and say, oh, that's my estimation. Like, for example, you want to see what you're going to be your grade for this semester. You can say, oh, last semester the grade was in average 70%, so I'm going to get 70% too. That's called blind estimation. But we don't want to do blind estimation. We want to do other methods to make it more precise. And we're going to learn those today. We started last class, and we're going to continue today. And this week, we're going to finish it. So we are still in estimation part. We talked about conditional mean. We're going to talk about covariance or variance as well, conditional covariance. And we also going to talk about something called mean square or mean square error or minimum mean square error when you want to optimize it. This is another method of estimation. This is another method of estimation we're going to learn today. In addition to conditional mean, we also can use MMSE or minimum mean square error. Mean square error, they are equal. Mean square error and conditional mean, we can prove that they are equal. Anyway, we're going to talk about that as well. Is lots of fun. So first of all, we need to see what estimation means. Estimation is actually like a theory that is kind of finding some unknown random variables. You want to guess some unknown random variables using some observations. Those observations not necessarily related to that random variable. Like, for example, you want to see what is your grade this semester. You can see last semesters, for example, people got 70% in average, but there is another variable there, how much they studied. So you have two random variables. One is the grade. The other one is how much they studied. So we have X, that is, you want to find it for this semester, but you have some information about last semester that, for example, in average, people got 70%, but they studied 5 hours per week. But you in this class is studying, for example, 2 hours per week. So what's going to be your estimation of your grade? So this is how we do estimation. We are not just doing blind estimation. We are not just look at the average of last semester and predict this semester. We also need to consider other variables. So estimation means we are estimating some unknown based on other observations, like that hours of studying, for example. That's another observation. We can observe that. So that's called estimation. The best estimation ever is actually, the best estimation is this. P of X given Y. This is posterior. If you remember, posterior density. If you max, the best X is arg max of this. And we're going to see that this is equal to expected value of X given Y. This is the best estimation ever. Why is the best? Because you want to estimate X, you observe Y. If you can find this expected value, you are done. But sometimes it's not possible because Y is not linear. And of course, Y and X are related, like the times that people are studying related to the score that they get, of course. But not always linear. In this case, probably is linear. Like if you study more, you can get better score. But not always is like that. So finding this relationship is very nonlinear and unknown things. That's why it's so hard to compute this expected value. But there is some ways. Sometimes we can imagine that this relationship is linear relationship. It makes it easier. Last week, we imagined that this relationship is a Gaussian relationship. And we realized that with this assumption, how everything got smooth and nice. Because assumption that we had for Gaussian relationship between X and Y makes to find a closed form solution. We did some tricks. For example, we computed actually block representation of the matrices and then computing the square. Do you remember that? We made it simpler to find this one. We computed this one last week, and this is the best estimation ever. If you can find this, you are done. In a closed form solution, closed form means not approximation, not anything, randomly is exact result. That's called closed form. And when you are dealing with Gaussian relationship, most of the time you can find this closed form solution, and that's great. But this assumption is not always true. Relationship between a score and a studying time depends so many other things. Maybe you have a stress in exam. Maybe you have other issues. Those also affect, it's not just time. So this makes this relationship not linear, not Gaussian. And in this case, what we can do, we can approximate it to linear. We can approximate it to Gaussian. We can sometimes do some methods to solve, to find this in different ways. Sometimes we can break that down to factors. Like we say, OK, this posterior density coming from so many factors. One factor is the studying time. One factor is the stress. One factor is the family issue. One factor is, I don't know, sickness. One factor is that. And then can solve it as well. That's another way. We call it factor graph optimization. So, but that's very advanced. We're not going to go with that. We're just going to, in this class, cover two cases. Linear relationship and Gaussian relationship. Gaussian relationship means x and y moving smoothly close together. They are moving slowly close to the mean, you know, like a bell shape. Linear means when x change, y change too. When it gets decreased, that decrease too. When it's increased, that increase too. That's a linear relationship. This is two cases. Application of this is a lot for predicting, for example, sensor measurements. When you want to estimate, you know, position of the object, when you want to predict, when you want to construct a signal, you want to construct an image. It's all estimation. You get the picture, and part of the picture is unknown. You want to construct it. That's amazing, isn't it? This is all estimation. You are tracking a drone, and drone going behind for example, trees or clothes, whatever, buildings. Still, you want to estimate it. Even though your measurements are not certain, your measurements are sometimes not clear. Even sometimes you don't have measurements, but based on the past, you can still estimate it. That's very good application of this class, that how using this, how we can solving x given y, and computing this, and break that down to the little pieces, we can solve these kind of problems and do prediction. Yes? Yes, no, they are same. Yeah, same. Prediction and estimation means same. Yeah. Sometimes we call it prediction, sometimes estimation. Yeah. So both same. So the idea is to find some unknown random variables using observations. But those observations not necessarily related to x. You know, the score that you are getting is not related directly to the time that you are studying. You know, it's not that. Something else is x and y, but related. They are correlated. They have correlation. And that correlation is important. Last class, we talked about correlation. We said when we have joint random variable like x and y, like, for example, x is a score and y is the time that you are studying, the covariance, the variance in this case is called, in a matrix form, you need to find the covariance of x related to itself. We call that sigma x. Sometimes we can call that sigma x, if x is more than one dimension. and sigma y, and sigma xy, and sigma yx. This is covariance. So anybody can tell me what is different between this sigma xy and sigma x, for example, or sigma xx? But both x and y are random variables. What is sigma x? A standard deviation. So what that means? Exactly, deviation around the mean of x. Okay? What about xy, sigma xy? Combination of them, or how they are related to each other, like how they are changing together, how they are changing respect to each other. Still around the mean, but how they are related together. So this is showing how x and y are depend on each other, or how relate each other, or how they change together, with respect to each other. How they change around the mean respect to each other. So that's a covariance. When we are talking about variance, we just talk about one random variable. When we talk about covariance, it means between two random variables. Okay? So when we have joint random variables, we always have this covariance. Sometimes these two are 0, so it means there is no relationship between x and y. X and y are not dependent on each other. Okay? But most of the time related. Like in this case, in this example, your score compared to a studying time related. Maybe you say, no, it's not related, but I think it's related. Normally, when you study harder, you get better score. Oh, why always this has a battery issue? I don't know. Need to change the battery. Any more questions? Right. Okay, this works. Okay, so let's go ahead. So lots of application with that. So what is the goal? The goal is to find the estimator. When we put a hat in top of x, this means this is the estimator. And is a function of y. Y is those observations. So we need to make our notations similar. I think last class notations were not similar to this, but this is the main. I checked the book, and they use the same notations. Sometimes we put z instead of y, but let's consider it y in always. Anytime I say xy means x is estimation, the hat in its top showing estimator, and y is the actually observations. So we want to find this estimator that is accurate as reality, as possible. And the best estimator, we already know that is expected value, but it's sometimes so hard to compute. But another estimator is this. What about if we have true value, if we have x, if we have ground truth, sometimes we call it ground truth, the x is ground truth, or the true value, or the something that we want to find through random variable or ground true. And this is estimator. Estimate of x, function of y. So if these two be close together, we did good estimation. This is our goal. We want to make this distance as this error. This is the error. We want to make that as less as possible. So, and why we make it a square? Because a square makes it positive, and it's kind of a little give more penalty to this error. So this is called mean square error. That's an error, that's a square, that's a mean. Mean square error. Anytime we hear this mean square error, we are dealing with this. And I want to mention these two are equal. Instead of computing this, sometimes you can compute this. That's easier to study. Expected value of a square, you can get derivative. You can put derivative equal to 0 and find parameters. You had this type of optimization before. So that's called mean square error. And if you want to minimize it, it becomes to MMSE, minimum mean square error. This is what we want to talk today. How we can minimize this error. This is the error. Why error? Because x is something, the true value, the ground true, and x hat is estimator, and we want to make these two close. It means we want to minimize this error. And this error, if we minimize it, if there is some parameters involved, we can find those parameters using actually derivative. We can use derivative for that and find it. I'm just going to check to see everything in this recording is OK. OK, good. Any question about these two? This is just, I want to mention what we're going to do. We need to compute this, but this is so hard. But if we compute this and make minimum of that, still we can find same results. OK, let's talk about conditional mean. We started that last week. Remember, we said conditional mean is the best estimator ever. And it's actually result of this expected value. We already talked about that. Let's do some intuition why they are related to each other. The reason coming from this. You know, x and y, x is the value that we want to estimate, like your score. And y is the random variable that you can observe. That's, for example, a studying time. And they are related to each other. They make a joint random variables. Okay, a score and a studying time, joint variable. Okay, and there is x. I want to see what is this expected value of x given y. But on top of that, we have posterior density of x given y. Posterior density is called posterior density. Posterior density, you are actually want to see posterior density of x given y. How this is also distribution. Yeah, this distribution called posterior distribution. how this is changing, how this posterior changing. This posterior changing around is x is a random variable. X is a random variable that is related to the y. And previously, we talked about the best x is when we are maximize this posterior, or argmax. And what is the maximum of this posterior? Maximum of the posterior is around the mean, isn't it? So this is equal to expected value of x given y. So there is a proof for that. We can prove it, but it's higher than, we don't need to go in the details. But the intuition is like that. So first of all, this is conditional random variable, as I explained here. Let I clean this up to explain that from here. So first of all, this is conditional distribution. If we pick some y that is too high, we're going to have a large error. If we pick some too low, still we're going to have large error. So what is the best one? The mean of that. So that's why the mean of this is the best result for that estimation. So these two are related, and they are actually equal. So mean square error estimation is equal to expected value of x given y. Let's do that for with more details. Okay, so mean square error is expected value of x given available information. At the beginning of the class, I mentioned that we sometimes can estimate without considering y. That's called blind estimation. Blind estimation is we don't care about the observations. We don't care about, for example, the other variables that involve. You just get average. Last semester, average was 70%. So this semester also probably you're going to get around 70%. It's not true. Maybe you get by chance, but it depends other variables, how much you are studying. Or maybe there is more variables involved, like your stress level, whatever happening in the exam. And that's going to affect that variable x as well. So if we do just blind, this one estimation, we call it blind estimation. Sometimes we have some events happening. So we can estimate x given some events. Like, for example, you want to see if you study, for example, more than 5 hours, or more than 2 hours. So you don't specify one variable. You don't specify one value. You specify an event. And in this event, for example, y is less than, for example, 3, something like that. It makes it, that's an event. You might have that. We don't study this right now, but we are studying this one. We want to find exact value. For example, you want to find your score if you are studying like exactly 4 hours. Studying time for that example. I'm just going to bring that example up to just understand what is x, what is y, We want to make it tangible. We want to make it understandable. without example, it's hard to imagine what's going on in estimation. It makes it a little complex. So in estimation, we have these three cases. Blind estimation, given some events, given some observations. Observations are observable, are measurable. You can measure them. You know how much you are studying. You can measure them. You can get average of them. Say, OK, every week I study 3 hours, sometimes 3.5, sometimes 4. When you get average, you know y, and mu of y, and even variance of y. This is observable. You can use some sensors to measure that. But x is not measurable. X is unknown. X is showing what is your grade. It's something unknown. You don't know anything about it. However, you know from last year, the x mean was around 70%. The variance was this much. And correlation was this much too from last year. You know that x and y last year changing like linearly, for example, with a factor of 50%. Like, for example, if you study 50%, like 2 times, you're going to get 50% more grade, something like that. You know this information from last year. Now you want to estimate your grade this semester if you study in average 5 hours. That's called estimation. I want in that discussion, you find some of these applications that you are dealing with in your project, in your classes, in your courses. Yes? Yeah. Right now, we don't work with event, but consider event a set of actually observations. A set of observations. Like when y is less than 3 is a set of observations. Yeah. OK, so that's estimation. So problem setup, x is unknown. We can't observe x, as I mentioned. We can't observe x directly. But what we can observe some events of x, some events of y, or some random variable y that, for example, that is studying time. OK, so we can observe that. So this gives kind of partial information. This is some partial information about x. Y is partial because other factors involved that we didn't consider. We just consider y, that is the time. But as I mentioned, so many other factors can involve. That's why I'm saying finding this E of x given y is so hard. Because this y is not just 1. It's so many other factors. We just consider maybe 1 or 2 or 3. But it can be so many other factors. But as far as we make it more precise or precision or prediction, going to be more close to the reality, more close to the true data, more close to the ground truth. And more to the, close to the ground truth means x minus x, y. This error is smaller. This is the error of our estimation to the truth value. How we can find this error smaller? We can minimize this mean square error. This mean square error is coming from here. Any question about mean square error? Maybe you'd say, OK, what is this x? We don't have it. How we can put it in formula? Yes, that's true. We don't have x. But still, we can put it in the formula and get derivative based on some unknown. Maybe you imagine this estimation is linear, Gaussian. If this is linear Gaussian, you can break this expected value down to the formula. Last week, we talked about it. We said expected value, if x and y are Gaussian, I mean their relation between them is Gaussian, x given y is equal to mu x plus sigma xy, sigma yy inverse y minus mu y. Remember this? We found this. Let's see what we have here, what not, okay? In here, we already know this. Mu x last year mean for that example, the score. We know this. Last year mean of a score. This is your observation that we want to actually, that we have that. Like, for example, you are studying 6 hours. You are studying 6 hours per week. And this is the average of studying. And what is this? This is the variable that we need to find. This is the covariance, and this is the variance. Variance of y and covariance. You need to know how you're studying, but from last year. You have all of them from last year. So you have some data to find all of those variables, and y is something that you are doing now. You are studying now 6 hours, for example, 12 hours, whatever. You want to see what is your score. You're just going to put it in this formula. Done. That's a mean. Even you can find the variance. Variance also we're going to compute it. Last week we didn't, but we're going to do that as well. This is when x and y changing Gaussian together. The relationship between x and y is Gaussian in this case. But if this is linear, how we can find that? We can do a little optimization and find that. Let's do it. How we can solve MMSE? As I mentioned, we need to do a little optimization. We know that we need to minimize this error. We need to minimize this expected value. Okay? So minimization of that, we need to know this. If you want to minimize that, you need to know how this estimation related to y. Is it linear relationship or Gaussian relationship? Whatever relationship exists, we need to find that and find it. To optimize that, after optimizing that, we can find this one. Is always possible? No, because sometimes x and y are like very complex relationship to each other. It's not always easy to compute. But it's always possible to approximate it. If relationship is not linear, we can use Taylor series, for example, to make it linear. If it's not always Gaussian, we can approximate it to Gaussian, for example. This is possible. So if we do this approximation, yeah, we are losing some precision for sure. But it still is much better than that blind estimation. You just get average of last time. That's not good estimation. Okay, so if we consider linear relationship, this estimation of minimum mean square error becomes linear minimum mean square error. We add one L at the beginning. If we consider this relationship linear, this is the relationship that showing the relationship is linear. Maybe you say, why you wrote this complex? Why you put mu? You just can write AY plus B is equal to X. Why you didn't write this? That's the same. Why I make it two variables, a and b? I just can consider one unknown variable here, a, but the other variables are given. From last year, we already know that mu x, not just last year, many years, for example, we have lots of prior information. Those called prior information. We know those. We know mu x, we know mu y, but we don't know a. And y is also given. Y is, for example, you are studying 6 hours, you want to see what is your grade. You knew that people before studying 5 hours and get 70%, but you are studying 6 hours. What is your score right now? Your score right now coming from this formula. If the relationship is linear, it makes sense to be linear. When you study more, you get better score. So you have this, you have this, you have this because it's 6, but you don't have A. So if you put this there, it's going to become an optimization problem. But because this is square, easily can get derivative and find this A, put it 0, and find A, done. That's how we do optimization. So let's do it. OK, before doing that, I'm going to switch to last week. We did this for Gaussian. We're not going to do all the details. We know that for Gaussian, we can do some trick, block representation of variance or covariance matrix, and computing the square, we find this. Is this familiar? Yeah, it's exactly like a y minus mu y plus mu x, isn't it? So A in Gaussian is just that formula. And what is this formula? Covariance and this is just a normalization factor. Because this is inverse, so it means go to down and make that normalized. It's all given. We know that. We know y. Y is something that is observable. We have enough information about y. We don't have information about x. We want to find those information about x. So normalization factor, covariance. Why covariance is important? Because covariance is everything. Covariance is showing how x and y changing respect to each other. If you're studying harder, are you going to get better score or going to get less score? That relationship coming from covariance. So this, I wanted to show that even though the relationship is Gaussian, but is very similar to linear. That's why Gaussian is so well-known and great, assumption. When you assume that relationship is Gaussian, so many things kind of get solved easily. You know, we can find a closed form solution. Look at how closed form. This solution is very nice. We call that closed form. Closed form is we find exact value. When we are dealing with an uncertain volt, finding an exact value is very rare and very hard. But assuming Gaussian makes that happen. That's great. Remember, we said everything is random in this volt. How we can find a closed form solution? Any response for that? That's a closed form solution. It's the exact value coming from that if you consider Gaussian. So what is the uncertainty here? Why I forgot to mention? Yes, but I said nothing in this word is certain. How we can find a certain value? What is wrong? Any idea? That assumption. I made a wrong assumption. I assumed the relationship with Gaussian is not always Gaussian. That's the part. If you assume that, you can get that. You assume something that is not always possible. You assume something that is not always true. So with that assumption, I can get this closed form solution. Yes, in reality, relationship between x and y is not Gaussian. That's why this solution is not optimal solution. We call this approximately optimal. Optimal means exact closed solution, closed form solution. Approximately optimal means you had some assumption. Those assumptions make it approximately optimal, you know. But it's very close to real ground true, of course. OK, that was something that we already explained. So in this, we have derivative from mean. We have covariance. And we have base. That's a base. So this is called innovation. You need to remember this name as well. Innovation. Innovation means how your score is actually related to average of previous. The time that you are studying, how much the time that you are studying deviate from the time that previous people are studying. Like the average was 5 hours, but you study 6 hours. So you study 1 hour more. So if you study 1 hour more, so this is going to add that mean a little bit. But this A, going to normalize it. This A, we're going to find this A. That is a function of covariance for sure. It's going to kind of normalize it. Any question about this relationship with linear and Gaussian? As you can see, they are very close. This was linear. That is a Gaussian. A, here we're going to find it using optimization that we're going to see is very similar to that. Actually, it's exactly similar. It's covariance and inverse of variance of y. Same. And how become same? This is amazing part of Gaussian assumptions. Gaussian is great. The big idea, we are kind of updating prior estimate using new information. The new information coming from this part. And the base is prior estimate. Prior estimate is, you know, the average of 70% passing the course. That's prior. How we update it based on this random variable that is the time of studying, that we know in average people are studying 5 hours, but I study 6 hours. I want to see what is my score. Everything down here, just A. We need to find A. In Gaussian, A is given too. But in linear, we need to find it. Last week, we didn't complete conditional covariance. Conditional covariance is sometimes we need that because we want to see if we estimate something, how good is your estimation? The covariance showing how good your estimation is. Like, for example, you are detecting a position of target, And you want to see how good is this estimation, how your estimation is close to real value. So that's coming from covariance, isn't it? So the covariance also can be computed in the same way with these tricking things that we mentioned, block representation of the covariance and computing the square. We can find the same way, very similar case. Why is similar? So still you have prior, covariance of prior, and we have some information minus those. What you can get from this is amazing formula. It's showing your uncertainty decreasing, isn't it? Because that is always positive value. This is always positive value. Quadratic form, isn't it? This is quadratic form, is always positive. So your prior covariance decreasing. If the covariance was, for example, big, so for example, this is your prediction. This is the target. For example, you have a system to detect the target, and you use radar or LiDAR, whatever. This is the target. You predict that it's around this area. And this is sigma xx, showing the ellipse around the mean. This is the mean, E of x, that we have from information that we have. And that's this. But the new one is smaller than that. If we find the new one is smaller. So it means you are more precise. That's a kind of proof that you get better after using those new information. Because your covariance gets smaller. Your covariance, when it's smaller, it means you are more precise. Because covariance showing deviation around mean, isn't it? If the deviation is smaller, it means your prediction is much better. If it's very close, it means your mean is exact value. So that's very important. That's very important, that showing estimation helpful. I mentioned here, this is smaller than that, and that's great. This reduction is coming from new information that's coming. Any question about this? Let's have another example of robotics to clear that more. You have a ground robot, the robot that's moving on the ground. It has some wheels. And the last position of that was, for example, x bar. The last position, we had last position and velocity. So we can predict if this robot moving with this velocity, and it was there, in 1 second is going to be in a new position. So that's how we do blind prediction or blind estimation. We just use past information to predict future. That's called blind estimation. But what about this robot has some sensors too, to measure some information, to get some observations, to find a new position as well, that is y. Right now, instead of having expected value of just x, we have a new information that's coming from these new sensors. And we update that prediction. We predict something. We predict something from before, and update it using new information. Those new information are this that makes our precision more precise, make our actually prediction more precise. Okay, so let's do one example. Last week we talked about this example. We said there is a x and y that are Gaussian relationship, and we imagine that is a robot position of the robot, for example, or drone, whatever, drone, for example. So x is unknown. So we have a radar, and we want to find the position of this drone. Okay? And this is x that we want to find it. But we have some observations. This radar gives us some observation that we say, okay, the y is previous x, or x plus some noise. Okay, some noise, and this noise is a white noise. This is a white noise. There is no correlation. If we call it white noise, it means it's circle, like that. Around the zero, mean is 0 and sigma is sigma w. That's a noise that we have. This is what given. So x and y have a Gaussian relationship. This is our assumption that makes everything simple. If the relationship Gaussian, the covariance or the variance matrix gonna be like that. This was sigma xx. This was sigma yy. That sigma yy is coming from because of that formula. We already talked about this last week as well. And sigma xy is equal to sigma yx is equal to sigma xx. Based on that, again, formula, if we put that. Anyway, there is some information given. So mu x is our prediction. We predict that drone is in this mu x with this uncertainty around it. And this is the noise. And this is the y. Y is the new value that we read from the sensor, from the radar or lidar, whatever. We had y. So how we can fix it? We can find the mean, and this mean coming from that. So everything is given. Everything given in these matrices, we just need to put them there, find this inverse, and find a new value. If we draw that, and covariance as well. For covariance also we can do the same. In this picture, you can see how big was. When we do prediction, this is coming from prediction or prior mean. And this is prior x, mu x, and this is the measurements. And these measurements help to find better estimation. This is estimation, x hat. So as you can see, if you draw those pictures, these values, if you draw it, you can see this covariance get smaller. This is exact application of whatever we mentioned here in that tracking, this is tracking problem. You are tracking something. You are tracking, you had some previous information, predicting something, and then get measurements, update it. Prediction, update, prediction, update. Is that familiar? Yeah, Kalman filter. I don't know, have you had Kalman filter in your life? I mean, your not yet? You're gonna see that soon. It's Kalman filter. We're not gonna finish it. We're not gonna talk about that in this class, but maybe in, because we teach this course for advanced too, like for grad students. In that, I will explain that as well. That's Kalman filter. Kalman filter is for a state estimation. You are estimating like position of the robot based on the previous information and new observations. But we are doing the same in a smaller case, but it's, imagine this is a state update. The state update, it makes a trajectory of the target. You're just predict it every step, update it, find a better one. A state update, and you find the trajectory of this target that you are saying, oh, it's moving like this. Okay, so that was a very practical example. Let's go for linear case. So we are done with Gaussian assumption. When we do Gaussian assumption, we can get closed form solution, very nice. The rest is just putting those values inside and find actually mean and covariance or variance. But what about linear? If the relationship between x and y is linear, we can write this formula. As I mentioned, this is exactly similar to I write estimation of x is a y plus b. But this kind of makes everything mixed. So a and b are mixed with this mu x and mu y. So we just consider that one variable, one unknown, a, one constant that we need to find. Okay, so if the relationship is linear, it means that. What is unknown here? Everything's unknown. Mu x is known. Mu y is known. Y is something that you know, like for example, you are studying 6 hours. You want to see what is, are you get better score or not? The y hat is the newest score that you're going to get if you study y hours, capital Y hours. The rest of those are, the only things that is not known is A. How we can find A? Optimization. So we find mean square error. We put that value inside mean square error. That's also very easy to compute. So I'm just going to very fast compute that. X minus x hat is equal, this is coming from this, x minus mu x minus a y minus mu y. So imagine, change the variable. Imagine this is a, and this is b. Sorry, not that, just this part, b. So a minus ab square is a square plus a2 b square plus 2 minus 2 ab. It's a square formula. So right now, if you put a x minus mu and y minus mu, this becomes sigma x. This becomes a2 sigma 2. and the rest becomes covariance, because AB. Because covariance of x, y is expected value of x minus mu x, y minus mu y. So this is coming from this kind of proof. Okay, so we have that. So what need to do now? You tell me. What is the next step? We computed MSE. That's a kind of formula. We have a squared minus 2a, something that is, we know that. Covariance is given. Those sigmas are also given. We have them all. Whatever we don't have is a. How we find a now? What is the next step? What is the next step? Can you guess it? How find A? Like that. I use time. How find A? Yes? Any? Are we trying to minimize it? This is error. This mean square error. We want to minimize it. Yeah? How find A now? That you know we want to minimize it. Did you minimize before something? How minimize things? What?
Make it small.
Yes. No, there is some, you want to find something to minimize it. You know, you want to find A that minimizes this formula. Derivative and equal to 0. That's great. Yeah, we need to get derivative and put 0 to find A. Because derivative becomes 0 when it gets minimized. Look at that. You want to find minimize of this function. You get derivative showing the slope. And when it gets 0, it means you are in a minimize. So we get derivative. We get derivative and put it 0. That's done. Derivative of this is very simple. That part is a constant. Go. We get derivative respect to A because we want to find A. We get the derivative respect to A, and A can be computed. What is A? A is a function of covariance. Do you remember I mentioned? This is always a function of covariance and sigma y squared. This is so familiar, no? It's exactly what we had in Gaussian. Good? Any question about that? Because I'm going to clean this up. Okay? So that's a final. And this is our final estimation. And it's LMMSE, linear minimum mean square error. You're going to see MSE a lot in your life, in your career, I mean. Minimum square error. And you always want to minimize it. Because it's a square error. You want to minimize error to be better, to have better prediction. Have example. This example is also very practical. Imagine you are testing a drone. You're working in a drone in your workplace, whatever, and they want to test how far this drone can go with some specific battery, for example. But there is some factors, and factor is wind. So you have two random variables. One random variable is a flight range, kilometers, for example. The other is a speed of wind, y. Y is the speed of wind, meter per second, for example, that can be observed. But you can't observe the flight range because it's something, depends so many other things. But one of them is wind. Okay? So, but we have some information. Those information coming from testing and testing and testing. We tested many times, and we realized that, first of all, is most of the time going 5 kilometers without considering wind. With this deviation, variance actually, and an average wind is 10 meter per second, and variance of wind is also 4. This is just data. We collected data many times before. But this is something nice. This is showing we have this as well. Based on the before, we tested so many times and times and times and realized there is a relationship between wind and flight range. When the wind gets more, range gets what? Less or more? The relationship is negative. So it means if x is get more, y get less. They are negative relationship. That's important. This relationship, this value is important, showing when the wind get more, x is get less. Makes sense that wind is too much. The drone cannot go fast because wind is against it, or it makes resistance, whatever. So what we want to find, we want to find this estimator. We are imagining that this is the linear estimator. So we find A. We already have A before. We computed A. We put that there. And we find the relationship. That's what we want. We want to find a function that estimates whatever actually wind we have, we find how much is going to go. Example, imagine wind is 12 meters per second. How far the drone can go? 3.5 kilometers. If we decrease the wind to 7, as you can see, it's going more. 7 kilometers can fly. That relationship is, this formula gives you all details. That's called estimation. Okay, next time we're going to talk about more crazy and application of probability in stochastic processes and random vectors. Any questions? Don't forget your discussion. Tomorrow is the last day for writing something and then answering somebody else till Friday. It has 1 score for your grade, remember?